there is something what is called specular reflection, and it's something when we have very smooth surface of something, and when light comes straight at a certain angle, it goes again at a certain angle. So it's just perfect conditions where light comes with angle incidence and reflects with angle of reflection. And there is very important rule again: angle of incidence equals angle of reflection. Yeah, it's just equal. And there is another situation which is called diffuse reflection. It's something opposite to specular reflection. It's something like this. As you can see, the surface is bumpy, and that's the problem. It's not about this law. We don't say that this law doesn't hold right here. In fact, it does hold still, but the problem is about the surface. And when the surface is like this, you can see that light is scattered. It's reflected in different directions. Yeah, that's why, for example, where you can see such kind of phenomenon. Well, let me show you this picture. Yeah, this one, and let me show you this picture. This one. Yeah, so basically when you look at the mirror, you see your perfect reflection, because all the light coming to your face, going to the mirror and reflected to your eye, you can see your face very perfectly. However, in this situation, when you get out of the bath, the room gets just hotter due to temperature, and there is a steam, and the steam sets on the mirror non-equally, and at some points, at some parts of the mirror, the steam, just the air molecules set non-equally. Somewhere there are more, somewhere there are less, and that's how you see something like this, because light is scattered. Light is reflected in different directions, not perfectly into your eyeball, and that's why you see something not very smooth. Yeah, but in fact this law still holds. Okay, let's move to problem solving. So basically, if we know that angle of incidence equals to angle of reflection, we can solve something like this. Very easy problems. So let's try to find this theta angle in this kind of situation. Basically, it's really easy. If you know that this is 65 degrees, we say that this is also 65 degrees, right? So if this is 65 degrees, we know this is 90. This would be just the left 25. We know that the entire any triangle would be just 180 degrees, and if this is 25 plus 120, it would be 145. This part must be 35. Yep, okay, different red, I'm sorry. Yep, this red, 35, and again, this is 90 degrees. If this is 90 degrees, it means that this part must be 55. Yeah, 55 degrees, and again, if this is angle of incidence, how light enters this part, it must leave the same angle. Yeah, this theta has to be also 55 degrees. Okay, good. Yeah, that's pretty good. I like it. I like it. It's really easy. We don't have to think much, but let's think about the second problem, which is more interesting. So basically what you have here is this kind of situation. Basically, you have lamp which shines at one wall of the entire room. And as you can see, non-equally, not on the entire wall, yeah, at a certain parts of the wall, something like this and this. Only this part of the room is shiny, all the other parts are dark, and we need to find what would be the entire X, yeah, what would be the floor range which is being shined. Yeah, so okay, so how do we just calculate it logically? If we see this kind of part, this part is entirely dark, this part is entirely black, and this dark, as well. So how do we solve this problem without any angles? In fact, we don't need any angles, we can make them ourselves, and let me show you how. In fact, we can use the law of Z, which comes from geometry. Yeah, this part is alpha, and then this is alpha as well. Yeah, and you can see we can make some this kind of normal from the wall, same thing here, and as you can see here, we have this Z shape, and we can have this, call this some alpha. If this is alpha, then this is alpha as well, and we know that rule, the angle of incidence equals to angle of reflection. Then if this is alpha, then this is alpha as well. And again, you can see here a large Z, this kind of, and if this is alpha, then this is alpha as well, right? So it would be alpha here as well. Yeah, good. What about, but it's only about one line of the light, because we're talking right now only about this line, only this line. We have also the second line, which is this one. Yeah, let's work with that. Let's forget about the first line and let's concentrate on the second line. This part, let's call it beta, right? If it's beta, then again, the rule of Z, this entire part is huge Z. Then it must be beta as well. Angle of incidence, angle of reflection, this is beta, and here you can see small z, again, here is beta. Okay, what it gives us is very important, because we can right now apply something like this. Okay, first of all, let's give some meaning to this entire part. Yeah, let's give some meaning to this. And let's give some meaning to this thing. Yeah. Why do we need it? Because let's call it some L1, let's call it some L2. And the thing is, it would be very easy for us to find x. X equals just L1 minus L2, right? And we need to give some meaning to L1 and L2. Basically, we can write something like this. How do we understand what is alpha? It's just this triangle, right? We can just apply, you can see the opposite side is 0.5, adjacent side is 1 meter, and we know the relationship between opposite and adjacent is tangent alpha, right? So we can write something like this. Tangent alpha equals 0.5 divided by 1. Yeah, because this is opposite, this is adjacent. And we know that tangent is opposite divided by adjacent. Okay, we have also the same principle right here. We have this entire triangle, this huge triangle. And you can see that we take these both things, 0.5 and 1 meter. That's why it has to be the opposite side of beta has to be 2 meters, not just 1.5, not just 0.5, but the entire 2 meters. And the adjacent side would be just 1 meter as well. So tangent beta must be something like 2 meters divided by 1. Okay. But I would not touch it yet. Yeah, I don't need to find this alpha, I don't need to find this beta, because at the end I can just make some proportions. Basically, in order to find L1, I can choose this this triangle. Can you see it? Yeah, this triangle, this huge triangle. Oops. And you can apply the very same law. You have the same angle alpha, and its opposite side is 2, because this entire part, 1.5 meters, 0.5 meters, it would be just 2 meters, and the adjacent side is just L1. So basically we can write this law like this. Tangent alpha equals opposite is 2 meters and divide by L1, because that's what our adjacent is. And the same thing we can apply right here, this small triangle. We have opposite, which is this 0.5, and the adjacent, which is L divided by 2. And that's how we got something like this. Tangent beta equals 0.5 divided by L2, right? Okay, so what we need here is L1 minus L2. We can give a meaning to this, yeah? We can write it something like this. From this formula and this formula, we can derive something like this. Let me write it here, let me write it here. It must be something like L1 equals 2 divided by tangent alpha, yeah? Because it's just a simple proportion. Here you have 1, and you make just, yeah, cross. Okay, so it would be 2 divided by tangent alpha. For L2, it's the same thing, 0.5 divided by tangent beta. Okay, but we know what tangent alpha is. We know what tangent beta is. We can just take it from here. We can just take it from here, and we can just put it inside. It would be just L2 divided by tangent alpha is 0.5 divided by 1, 0.5 divided by 1. Well, it changed nothing. Just L equals 2 divided by 0.5, which is just 2 divided by 1 divided by 2, right? And it gives us L equals 4 meters. Here we have tangent beta. We can put tangent beta here, 2 divided by 1, which is just 2. L2 equals 0.5 divided by 2. And L2 would be just 0.25 meters. Yeah. Okay, and if we just apply it right here, x is going to be 4 minus 0.25, 3.75 meters. So basically, the range of the floor which is being shined is just 3.75 meters. Okay, that's the answer. We just applied basic geometry rules, because that's what our main chapter is, geometric optics. Okay, right now we have something called Snell's law. Yeah, it shows us if some light comes at a certain angle, then it's going to be refracted at a different angle, because the medium slows down that coming light. And when it slows down, it changes its direction. Okay, so we can prove it mathematically. Let me write some proof. It's in fact not that hard. We know this basic formula, which is velocity equals x divided by time, right? Yeah, it's pretty easy. But also we can write velocity equals lambda divided by period. Yeah, because when we talk about the waves, yeah, we can apply lambda instead of x, and we can apply period instead of time. So this law still holds. It's the very same thing. Okay, and what also? We have something like this. Velocity is also c divided by n. So n is the refraction index of the medium. Okay, so c is the speed of light. Okay, good. What we also know about this is very important. We know that 1 divided by period is just f, which gives us the idea that v might be also lambda f. Okay, and this is very important. Let me just highlight it with a green. Yeah, this is something what we are going to work with. And right now, let's say I want to find out the relationship between two lambdas. Yeah, let's say something like this. Let me show you something, a relationship between lambda 1 and lambda 2. Let's say we have different wavelengths. And we have here what? Velocity divided by frequency. It would be v1 divided by frequency, v2 divided by frequency. The frequency would be the same because the light source shines the same, which means that frequencies does not change and they cancel out, and then we have just velocity 1 divided by velocity 2. The velocities would be different because one medium can slow down the light speed. Yeah, because 3 multiplied 10 to the power of 8 is the speed of light in the vacuum. Okay, not everywhere, only in the vacuum. And also, it might be in air, but because air has very low slowing down abilities. Yeah. So you can see this tendency. Yeah, this is pretty good. You can apply another rule, which is c divided by n. Yeah, index of refraction. So we've got something like this. V is going to be c is constant, n1, c, n2. And you can see that this constant just cancel out, and you'll have something like n2 goes up, n1 goes down. And you can just make a cross. This thing goes here, and this thing goes here. And you will have something like this. Lambda 1, n1 equals lambda 2, n2. Okay, yeah, that's good. There is also one interesting rule which we are going to talk in the wave optics chapter. Yeah, and this is lambda equals L sine alpha. Yeah, we're going to talk about this a little bit later, and if we apply it, it would be just L is, again, constant, it's the same length, and sine alpha 1 and 1 equals L sine alpha 2 and 2. And if we just cancel L and L, we've got exactly what we need. This is N1 sine, let's write not alpha but theta 1 equals N2 sine theta 2. Yeah, that's exactly what our Snell's law is. Okay, let's talk about a little bit total internal reflection. This is something very interesting. When our laser is inside of the water, yeah, not only inside of the water, but basically it's the best example to explain you, and it stands at a certain angle. In fact, it doesn't do only one thing. It doesn't just reflect or refract. It does both of the things, but at different angles, it wastes different energy for one of the things, right? So basically, when your laser shoots upward, in fact, it does 99% of energy, so the water didn't refract it. Yeah, so that's why it goes straight up. Only 1% is getting just reflected. That's why the light beam is not being refracted much. In fact, you can't even notice it, to be honest. In this situation, you can see something very interesting. For example, let me take this yellow. This thing is going to be refracted like this. You can see this refraction pretty well, but at the same time, it has also its reflection. Yeah, let me write it something like this. It would be better because it doesn't reflect much, to be honest. At this situation, it gets even more refracted. However, it wastes also a little bit more energy, so it was reflected. At a certain point, it gets refracted so much that it goes straight with the surface of the water that you can't even see. But however, most of the energy goes in order to it was reflected. You see this line? So these lines can be the same length, anything, but the problem is with the angle. This angle theta, we always take the angles relative to normal. This is very important. Don't forget it. So this angle is different, this angle is different, and this is just 90 degrees. That's why in formula you've got 90 degrees at the second situation, right? Okay. However, you can see this size, this angle, this angle, this angle, they are always work with the principle of incident line and reflected line are the same angle. This principle works still, but it's not the problem about the angles, it's the problem about the length of the line. So in this situation, you can see that reflection is not that much. In this situation, it's better, but in this situation, it's totally reflected. And that's why we call it total internal reflection. It's totally reflected. Okay? So, yeah, that's the thing. We don't need to prove it yet because it comes from the Snell's law. And at a certain point, this angle gets refracted so much it becomes 90 degrees, right? And where do we use it? We use it in fiber optics. What is fiber optics? In fact, it's the small wires that carry light. Yeah, so in fact, something like this. Light goes inside like a ray, and then it gets refracted totally inside. And you make light from one point. Yeah, this is light source. And then you receive light from this part, in fact. And why do we need it at all? In fact, it's the thing that makes your internet work really fast, because the fastest speed is the speed of light, definitely. Yeah, and in fact, when you use your any digital platform or ChatGPT or YouTube or anything, the fact that everything is being conveyed, yeah, in the servers of the USA or any other country which is really far from us is due to fiber optics. We've got something like the audio information. It turns into binary code. You know what binary code is? It's just 1 0 1 0 0 0 1 0 and so on. It converts into light information. Yeah, it might be just light info. It might be just an ordinary 1 is light, 0 is darkness, and so on. Basically, it's pretty easy. And this info, light info, goes through the wires. Then it goes from the other side. It transforms again to binary code. Yeah, it turns to the initial code like this, and then it's being conveyed in the servers, which are really powerful computers, and these servers convey the information, they work with the information, then they turn your answer into binary code. This binary code goes to fiber optics, to fibers, and these fibers go to light info. Again, this light info is transformed into digital binary code, and this binary code again goes to audio, which is pretty good. Yeah, this is the simple way of explaining fiber optics. Of course, it has its complex principles, but this is the simplest way to explain it, yeah, without any kind of complex problems of the fiber optics. It's the simplest explanation. Okay, right now let's try to solve some problems, so it was a good practice to you. For example, we have this kind of a problem. We have a right triangle, yeah, and you can see that the light is going through this prism, let's call it, yeah, and when it comes out, it's getting refracted, as you can see. But what would be the index of refraction of this kind of material? In fact, N2 would be 1, yeah, right? Okay, let me write one thing. Yeah, I have forgotten it, I'm so sorry. Yeah, basically, we have something also called critical angles, yeah? This is the angles which, yeah, let me write critical angles. This is the angles after which the light goes totally reflected, yeah? Before that, they can both reflect and refract, but after a certain angle, they can only reflect inside. And let's count it for water, and let me tell you that the index of refraction of the air and air is just 1, and in water is just 1.33, yeah? And we can just apply these numbers, which are really easy. The first, it was in water, so it has to be 133 multiplied sine theta 1 equals, it tries to go to the air, that's why it's 1 sine 90 degrees, which is also, this thing comes to be 1, and sine theta 1 goes to be 1 divided by 133. Yeah, and if you just apply it, if you use arcsine, it would be just 1 divided by 133, and angle has got to be something about like 48.75 degrees. So after 48.75 degrees, light gets totally reflected inside of the water. It cannot escape. It cannot escape to the air. It gets totally reflected inside of the water. Yeah, good. And for different materials, you've got different critical angles. Okay, for this situation, yeah, let's try to use Snell's law. However, we need to identify one very important thing. As I've said before, we always talk about the angles relative to normal. Yeah, normal line. That's why we need to write down here the normal line. What would be the normal line? It's always perpendicular, so it has to be something like this. Yeah, it's perpendicular to the surface. It's got to be something like, yeah, let's call it like this, normal, and let me continue it something like this, the continuation of the line. And it has to be 90 degrees, just like this or like this. Okay, that's good. What can we do with this information? So basically, let me just delete this light because we need just one of them. We don't need the second light because it's a complete copy of the first one. However, what can I do with it? I can do this very important thing that I can see that this is 90 degrees. I can see that this is 90 degrees as well, and I know that any triangle is just 180 degrees, as I've told you before. It's 30, it's 90, then definitely the third side has to be 60 degrees. However, I don't need this 60 degrees because what I need is this angle. This is 30 degrees, because you know, as I've said before, this has to be perpendicular, 90 degrees, okay? And 90 minus 60 gives us 30. So our light goes with 30 degrees relative to normal, okay? And what would be the angle of refraction in this situation? It would be this entire part, because our normal has to touch our reflected line. Yeah, this entire angle called alpha is going to be our angle of refraction. Yeah, so we know this is 20 degrees, but also 22 degrees, but also we know this rule, which is if we have this kind of situation, the law of opposite angles, this is got to be 30 degrees as well, so this alpha has got to be 52 degrees. Okay, if you just apply it, it would be something like this. Let me write it. N1 has got to be our glass. We need to find it. We don't know. N1 has got to be our glass. Sine, what? 30 degrees. It enters with 30 degrees relative to normal. Then N2 has got to be what? It's just 1 because it goes to the air. It's 1 sine 52 degrees because it's the angle of refraction. Okay, so basically it's got to be N1 equals sine 52, I'm sorry, 52 degrees divided by sine 30 degrees. Yeah, and it's probably, if I'm not mistaken, if I remember it correct, it's got to be just 1.6 degrees. Yeah, something like this. Okay, yeah, this is pretty good. Yeah, pretty easy, just for the training. Right now, let's try to solve this kind of situation. Yeah, let's say you, let's say this is night. Yeah, you have dropped your goggles to the pool. Yeah, and it lies somewhere under the pool, you don't know, and you don't have any flashlight, but you've got a laser. you know that the laser beam is very thin, very small, but still you can use it to find your goggles. And if you just shine your laser, you know that when you shine it to the pool, the water starts to refract it due to index of refraction, you know it. And you need to find this distance before it enters the water and after it gets refracted. You need to find this horizontal line, how far it is. So basically it's a simple geometry again. It's not that hard. In fact, what we can do right here is just find this angle. Yeah, let me show you that this is some triangle. This is some triangle, and we know exactly what this is. It's just below 2 meters. It's got to be 2 meters, and we know this opposite side, it's 1 meter, and we take this alpha. Okay, so our tangent alpha is going to be 1 divided by 2. Yeah, because opposite is 1 and adjacent is 2, and alpha is going to be arctangent 1 divided by 2. Okay, yep, not bad, not bad. But that's not the thing that I really need, in fact. If I find this angle, yeah, this alpha, it's going to be some number, yeah. I don't know what number it is. Let me just right now calculate it. Arctangent 1 divided by 2. Yeah, it's going to be 2657. It's going to be 26.5 degrees. Let's call it like this. But I don't need this 26.5 degrees. What I need is this angle. Why? Because, as I've said before, the incident angle would always be the angle relative to the normal. Yeah, we could apply it in different way. We could apply this 2 meters, this is 1 meter, and we could use this as our opposite, this is our adjacent. Yeah, but you can do both of those things and it's the very same principle. So we can just subtract because we know, we know that this is 90 degrees and this angle theta, let's call it like this, theta is just 90 minus 26.5 degrees, and it's got to be something like, if I'm not mistaken, 63.5. Yeah, am I correct? I guess I'm correct, yeah, 63.5 degrees. This theta has to be 63. So if this enters with 63 degrees, we need to find this angle, which is theta prime. Let's call it like this. And right now I can apply Snell's law. It's got to be n1 sine theta equals n2 sine theta prime, right? And I need to find that sine theta prime, which is sine theta prime equals n1 sine theta divided by n2. And theta prime is going to be just arc sine of this thing. n1 sine theta is going to be 63.5 degrees divided by n2, which is just, okay, n1 is the air, it's just 1, and water is 133. Yeah, it enters the water, that's why the first index of refraction is just air, it's just 1, and the second one is water, that's why it's 133. Okay, let me see what it's got to be, something like, so arc, okay, sine 63.5 degrees gives us 0.89. Okay, and we can divide it by 1.33. It gives us 0.67. Okay, okay, 0.67, and I need to use arc sine 0.67. It's got to be something like 42 degrees. So theta prime is going to be 42 degrees. Yeah, this angle is 42 degrees, and definitely we can use again this law of triangles. This is triangle, this is opposite, that is adjacent, and we can again apply here just tangent theta prime, which is opposite just x, and the adjacent is 3. This is opposite, adjacent is 3. Okay, and in order to find x, I can just 3 multiplied tangent theta prime, and x got to be 3 multiplied tangent 42 degrees. Okay, so basically tangent of 42 degrees would be 0.9 multiplied 3. It's got to be something 2.7. Yeah, so x is going to be something like 2.7 meters. Okay, so this is 2.7 meters. Okay, yeah, I like it. It's pretty good. Yeah, a good training